Hi, today I will be discussing Heat2Power's mission of integrating our high-efficiency thermal photovoltaics into thermal batteries. Thermal batteries offer a way of deploying large-scale, cost-effective, multi-day energy storage for a cost per unit energy of less than $20 per kilowatt hour, a substantial decrease compared to lithium-ion. Electricity is stored as heat in cheap, earth-abundant, and domestically available materials such as graphite, up to temperatures of 2400 degrees Celsius. An advantage of thermal batteries is that they can be discharged in multiple ways. Its small footprint and modular nature enables discharging as on-site high-temperature process heat, which has been demonstrated by companies like Antora and Rondo Energy from their megawatt-scale batteries. The second discharge mechanism is through electricity, which requires the use of thermal photovoltaics to convert high-temperature radiation back into electricity. At Heat2Power, we propose the development of a cogeneration thermal battery that leverages our breakthrough air-bridge thermal photovoltaic technology to offer a half to 1 megawatt of electrical and thermal output, with an estimated electrical efficiency of 40% and a total combined heat and power efficiency of 80%. This heat and power requirement matches the vast majority of industrial facilities across Michigan, and further compares favorably to other cogen technologies like natural gas reciprocating engines, when considering factors like efficiency, cost, and environmental pollution. Despite their numerous advantages, thermal batteries have yet to gain traction due to the low round-trip efficiencies incurred from using commercial TPVs, which convert heat to power at a max efficiency around 20 to 30%. In conventional TPVs, only about 20% of the photons have high enough energy to generate electricity in the photovoltaic cell. The remaining 80% low-energy photons can parasitically absorb and get converted into waste heat. At Heat2Power, our team has solved this challenge by developing the air-bridge thermal photovoltaic cell, which implements a thin air layer underneath the semiconductor that acts as a near-perfect mirror, recycling low-energy photons back to the hot-emitting storage medium. When first implemented in 2020, this method led to the highest recorded TPV efficiency of the time. Since then, we've made substantial improvements in semiconductor and cell design, leading to efficiencies of 44%, a 25% relative increase compared to competitors. Because cost per unit energy scales inversely with efficiency, this leads to dramatic reductions in costs. Additionally, we've scaled the cell from 1 millimeter to 1 centimeter. Our mission at Heat2Power is to build TPV modules from series-connected 1 centimeter cells using a 4-inch indium phosphide production line. These modules can be directly integrated into a 60-inch panel, the industry standard for conventional photovoltaics. Integrating our air-bridge TPVs into thermal batteries enables efficient cogeneration of power and heat. Compared to our competitors, our high efficiency and high power density cells will lead to substantial cost savings for thermal batteries, making thermal batteries an even more attractive option compared to competitive battery technologies.